Hello everybody. Today we're going to continue on with Chapter 15, the last part of it. We're going to talk about bandpass filters and a couple of other types of active filters that have more than one op amp in them in one case for sure. You can, we've kind of looked at low pass filters and high pass filters. The Bessel is what we did last. Bessel filter. A lot of times we'll do a Butterworth filter instead, and you know that's all based on those Bessel tables and what the feedback resistors are set up for, and you can just go to those tables and on the exam, which we have next week, you'll be presented with that table. You won't need to look it up. Of course you could because it's open book, but you'll be able to have that right on the exam. Anyway, you can make bandpass filters out of low pass filters and high pass filters, right? So you can pass, like showing here, a low pass response and then high pass response. These are probably flipped around a little bit. This should be high pass response over here and low pass response over here. And you put those in cascade and you end up with a bandpass filter. The problem is that they haven't got very good Q, meaning that the slopes on the sides of these, this like minus 40 dB per decade, which would be it's 20 dB per decade per pole. So that's a two-pole high pass and a two-pole low pass over here. Bolted together, you don't get that, you end up not getting this response, okay? So we do other things. We have a different technique for a different circuit that we use normally for bandpass filters. And that is this one here. This is a multiple feedback bandpass filter. It's only one op amp, so that's cool. But check it out. There's 2 capacitors and 3 resistors. Now, without doing any math yet, let's just see how this works. Remember, capacitors are short circuits to high frequencies. So what happens at high frequency? Well, this capacitor here, C1, becomes a wire, a short. Same with C2. It becomes a wire, a short. Well, if you remember what the formula is for just a inverting op amp, where you feed the inverting input, that's what this ends up being, except that R2, which is the feedback resistor, ends up getting shorted out by C1. And C2 is just a wire at that point. So you don't get very much gain at high frequencies, okay? So that is this part of the curve. At high frequencies, your gain goes down, okay? Let's look at low frequencies. Well, low frequency, sure enough, R2 comes back into play, sort of, because C1 is an open circuit. C2 is an open circuit too, though, right? Well, what happens is op amp's not getting anything because this is no longer a connection here. C2 at low frequencies is an open circuit. So that is this part of the curve. So at low frequencies, you don't get anything. All right? So that's a multiple feedback bandpass filter. Very common, okay? It doesn't have a whole lot of Q because it's only really one pole per side, one capacitor resistor set per side. Notice these resistors here, I think they talk about that here. This R1R forms an attenuation network. So your gain takes a hit from this too. The reason is because at the pass band, where everything's happening here, what can happen is you can saturate the op amps. You have to be kind of careful. There are design techniques. There's actually formulas you can Google, multiple feedback bandpass filter calculator, and you just put in your frequencies and it'll dump out some component values here for you. But here's some equations if you wanted to do it by hand, and you should put these on your equation sheet. This is the center frequency, so this would be the F0 is the frequency right in the center, right? So this is F0, right? And then the gain at that center frequency is determined by R2 over 2R1, R2 over 2R1, okay? Pretty simple circuit. Not too many parts. Here's one that doesn't look like a very simple circuit. It uses 3 op-amps. It is a state variable filter. Okay, but the cool thing about it is that you get a high pass output right here out of the first op-amp. You get a low pass output out of the last op-amp, and in the middle, you get a band pass output. So we have a summing amplifier that sums the output of the bandpass filter, a portion of it, it's divided by this resistor divider, back into this first op-amp, and then you also have an integrator. 2 integrators, one on the output, and this bandpass function here is formed with an integrator as well. Okay. We actually do a lab on this in the regular class. I'm not so sure we have it in this one, but it does tend to be a little tricky because there's a lot more parts, but it does work. We do eventually get it working. This one has a much better Q, much better performance, a much tighter bandwidth, works much better. Plus you get these other outputs. You can form a notch filter. I think that's what, okay, so the Q is given by this formula here, R5 over R6. Let's see what happened to R5. Okay, here's R5 and R6 down here. R5 divided by R6 plus 1 times 1/3. So we build this in multi-sim. This is a multi-sim circuit. And we show the Bode plot here, I think, and there's your bandpass output. And this is in fact exactly what it looks like in the lab when we do it in the lab. Okay, you get this Bode plot. You can do a notch filter, so I was getting to here, by summing the low pass and high pass outputs of your state variable filter. And you end up with a band stop input. So you can get high pass and then you get low pass, right? I guess to you it'd be low pass and high pass the way I'm facing. And you get a notch. So that's a band stop filter or a notch filter. You sum these 2 outputs into an op-amp. And this is a summing circuit. Remember those from a chapter or 2 ago? And let's see, we are doing that here with this summing amp. Here's the summing amplifier. We're summing the high pass and the low pass outputs and looking at it on the Bode plot. Multi-sim, and there you go. That's what you get. Now this is an interesting technique for getting Bode plots on an oscilloscope. Normally you can't get Bode plots on an oscilloscope. That requires a Bode plotter or a network analyzer. But you can actually do it by using a sweep generator and a sawtooth source. So this sweep generator has, you can either feed it with a sawtooth input, which is a ramping voltage, drops back down to 0, ramps up, down, and that controls the frequency. Okay, so it's a voltage controlled frequency. That's what a sweep generator does. That voltage output is an AC voltage, and frequency that comes out that's changing in frequency. So as the, it's frequency modulation is what it is. So as the voltage ramps up, okay, right here, you get a higher frequency. And what you can do is you can put your scope into XY mode, like we did before, to do the Schmidt trigger, remember? And the X sweep left to right here is controlled by that ramp. And then the amplitude of the signal is controlled or is measured with the Y. And here's your filter that you're trying to measure. So as this frequency increases, it changes. The filter's going to either attenuate or allow the signal to go through. In this case, this filter is a bandpass filter, as shown here. We get a F0 frequency somewhere in the middle of the scope. And you have to fiddle with this a little bit, obviously, to get everything tuned in. A better way, I think, well, maybe not a better way, but another way, a little simpler way to do it is to just take a regular frequency generator, okay, and get close to F0. Get close to F0 wherever you think. Just find out where the peak is, and you can even use a voltmeter on this. Just find out where the peak voltage is, and then turn your frequency down just enough so that you get 70% of what the peak is, and that'll measures the first cutoff frequency. Then you go back to the center with the frequency back to F0, and then keep going higher until you get 70% again of that peak, and that measures this part, the high frequency cutoff. Okay, and with that you can just plot it if you want. And that's normally how we do it in the lab with the scope. We don't normally use this, although we could, we don't normally do this setup. Okay, all right, that's it for this last part of Chapter 15. If you have any questions at all with regards to this chapter or the upcoming exam, just shoot me a message and I will jump right on it. Okay, good luck. Bye.